Welcome to our lesson on our third chapter in our environmental chemistry course. We'll be discussing the concept of global warming. We'll be addressing what is global warming and what can we do, if anything, to either stop it, prevent it, or reverse it. Is there really any cause for alarm? And how can we assess the information from the popular press? So we will explore global warming in terms of what is the major contributors and why should we care. You know, this is an interesting picture of some chimpanzees on the front cover page here in your textbook, and it's going to simply discuss the process of adaptations. You know, it's the chimps, they don't argue with one another if the climate is changing, as we as the population is doing at the moment. It's a very political hot button. They adapt in order to obtain enough calories to survive. So is CO2 the culprit of changes in the Arctic, which is considering the melting of our glaciers? And is carbon dioxide playing a key role in keeping the planet comfortably warm and yet able to support life, which is a very true statement, but can too much be bad? And what are we doing to really significantly change the environmental composition of our atmosphere in terms of the carbon dioxide role? So, of course, carbon dioxide, we drew its molecular structure before. We know that it's an O double bond C double bond O, and this particular molecule, with its shared pairs of electrons and lone pairs of electrons, this particular molecule is a hot topic for debate right now in terms of greenhouse gases. What is it about this molecule that when it's trapped in the atmosphere and its concentration begins to significantly rise, warms the atmosphere, warms the environment, and might even be contributing to some environmental changes in melting of the glaciers? So as we begin exploring these concepts, these debates, we have to evaluate the effect of the emissions on our climate. So the debate in its entirety is quite lengthy, and one scientific research can prove or disprove, depending on your political party. The debate of CO2 being released into the environment isn't if it's harmful. We all will concur that CO2, when emitted into the atmosphere, is harmful. It's just that we don't agree about how much is too harmful to live with. We all will, no matter politician or scientist alike, we all will agree upon we are emitting more than ever carbon dioxide. What we just don't agree upon is the level that is dangerous. Some politicians, some people might believe that the CO2s that are being emitted will not harm the environment. Some will agree that we are on the way to harming the environment. So we need to find out about an energy balance. And how are we altering that energy balance? We'll begin exploring things like the greenhouse gases and the greenhouse effect. Very specifically, how carbon dioxide, methane, and water vapor all are greenhouse gases. The molecular shape in this chapter will be explored, and in particular, the vibrations in the molecule. So just to kind of see this lesson as we begin to explore it later on, it's the actual bonds between the carbon and the oxygen atom, and the bonds in between this carbon and oxygen atom that serve as the absorption site of this UV radiation coming from the sun. So these particular bonds hold in energy, and therefore the more and more and more carbon dioxide in the atmosphere, the more heat energy we're storing in the atmosphere. We'll talk about the carbon cycle. Where do we find carbon, both in the atmosphere, in the earth, in the water, and so forth? We'll start to quantify in terms of atomic mass and moles. The moles is a measuring unit to determine how much we have in the environment. And we'll conclude with the discussion of the atmospheric gases and the aerosols and the roles that they play in environmental warming, known as the greenhouse effect. I'll ask that you pause the video lesson right here and go into your Blackboard site and just listen to some of these video clips that help set the stage for our future talk here. So just pause, Click on these, they're in your Blackboard site, and come back once you have a great idea of what the greenhouse effect is and how carbon dioxide is the culprit. Come on back when ready. Welcome back. Let's begin discussing the Earth's energy balance. We'll talk about how Earth is heated and cooled, and in terms of the Earth receiving nearly all of its energy from the Sun, primarily in the UV, the visible, and the IR radiation spectrum. So let's remember what we've learned from last chapter. We have this very tiny range that we call the visible spectrum. This is our electromagnetic spectrum that we studied last chapter. This is where we talked about Roy G. Biv. So this tiny little area here is the electromagnetic spectrum that we can actually see, called the visible light range. Remember, this was an approximate about 10 to the -9th meters, which is what we referred to as a nanometer. And as we began increasing wavelength, longer wavelength, we had a type of radiation known as IR, and then we even went a little further down just to kind of review with you these radio waves. So these are much longer wavelengths, lower energy. And as we begin looking this direction, going in a higher frequency or higher energy, we had something called UV radiation, about in this range here. So IR is less energetic than the visible spectrum, and ultraviolet UV radiation is more energetic than the visible spectrum. And then, of course, we went X-ray, gamma ray, and so forth. So here we are increasing energy as the wavelength shortens, and here we are decreasing energy as the wavelength increases. Where we're referring to for the Sun, primarily giving us energy, is in this particular spectrum, the ultraviolet, the visible, and the infrared area on the electromagnetic spectrum. The UV, remember talking about UVA, UVB, and UVC last chapter, UVC being the most penetrating but never reaches the Earth's surface due to being absorbed by ozone molecules. Infrared radiation, which is less energetic, does reach the Earth's surface and helps to keep an environmental climate suitable for life on Earth. So the Sun primarily in the form of UV, which is ultraviolet, very high energy, the visible spectrum, which is in the middle of the road, and the infrared radiation, which is of low energy, all comes to us from the Sun. The ultimate source of all energy reaching the Earth is from the Sun. Some of this is reflected right back into space by dust particles or aerosol particles on the surface of the Earth. 31% of all energy just bounces right back by hitting something else, ricocheting back to the outer atmosphere. The remaining 69% of the radiation from the Sun is absorbed, and it's absorbed by the atmosphere, those particles that are gaseous, or by the land, or by the oceans. So about 1/3 gets reflected back, a little more than 2/3 gets absorbed. The average temperature of the Earth would only be about 0 degrees Fahrenheit if not for the atmosphere absorbing radiant energy. Now we know that 0 degrees Fahrenheit, that is significantly too cold, and it certainly wouldn't be an ambient temperature to support life. So we can see a significant reason to want to trap the Earth's, energy from the Sun into the atmosphere to warm it up into a more desirable climate to inhabit. So in order to maintain the Earth's energy balance, and that's the key word there, isn't it? Balance, all of the radiation that's absorbed from the Sun must eventually go back into space. That's what balance means. What's hitting the Earth and being absorbed eventually to create a balance has to be equal but opposite of what is reflecting back. And so this is what the concept is with the greenhouse effect. The 46% of the Sun's radiation that's absorbed by the Earth, kind of breaking that down further into these two percentages, The Earth re-emits all of the radiation it absorbs, but at a longer wavelength. 37% is absorbed by the atmosphere, 9% escapes back into space. So let's think about that. If the sun's radiation is absorbed by the Earth, and remember we had UV, we had visible, and we had IR, infrared. All of the radiation that's absorbed gets re-emitted in this form, a much longer wavelength, which is less energetic. So we absorb high energy, but re-emit lower energy from the atmosphere. 54% of the sun's radiation is absorbed by the atmosphere, 23% reflecting back, 25% reflecting from the Earth's surface, about 6%. So all of these percentages can be visualized with this particular slide, and this is very helpful in kind of getting an idea of the word balance. Whoops. So here we have the sun and 100% of its radiation coming towards the Earth. Now let's take a peek at how it's being manipulated. So here we have, let me bring this back up, 100% of it coming down. See how it begins to split? Soon as this is the atmosphere of the Earth, remember here we had the troposphere and the stratosphere and the mesosphere, we start to hit these particles of gases known as our atmosphere. And as soon as some of this radiation hits, it reflects right up, back up. So as soon as it hits some of these particles, about a quarter of it reflects. Here, it might hit all the way to the Earth's surface, about 6%, and then reflected. Here, some of it is actually absorbed by the Earth's surface. About 46% goes into the Earth's surface, warming up the Earth. And about 23% is absorbed into the atmosphere, and that's where we're saying when we say absorbed into the atmosphere, they're literally being absorbed in the gas molecules' bonds, and we'll see that so critically important that there's certain gases in the atmosphere that the bond serves as a storage tank to place energy. So we're absorbing heat and keeping it close to the Earth, kind of like a blanket of heat. Some goes into the Earth, same idea. If it's going into the Earth, it's being stored in chemical bonds. But if it's reflecting, it hits molecules with an indirect pattern, not directly hitting the bond, but indirectly, and scoots right back up into the Earth's atmosphere. And we'll just take a look at 9% emitted from the surface, 37% absorbed into the atmosphere from the Earth's surface. This is it all returning, and then 60% emitted from the gases in the atmosphere. Once these bonds release the energy, it goes right back up out into the mesosphere. So to create a balance, our atmosphere gases trap and return a major portion of the heat radiating from the Earth. It's a natural, necessary process. To keep a balance, what we're looking at is all the arrows pointing from the sun down to the Earth. All of those percentages must add to an equal but opposite return of the energy out of the atmosphere. And that is what we refer to as an energy balance. So this greenhouse effect. Have you ever parked a car with windows closed on a sunny day? My goodness, here in South Mississippi, you can't help that. What might be a way that this phenomenon illustrates the greenhouse effect? And just pause and think about that. Think of a car parked on a sunny day with closed windows. How might that illustrate the greenhouse effect? When as soon as you open your car door, you certainly know it's warmed up inside. All of those surfaces inside your car, could be the seat cloth, could be the dashboard plastics, what it is, they're all absorbing heat and trapping it inside the actual materials. And it's the materials that are holding that heat energy, creating an atmosphere that's much warmer inside versus outside the car. Trapping heat energy is exactly what the greenhouse effect will do. And that's what our atmosphere does. It stores heat energy inside of the chemical bonds of the gases found in the atmosphere. So this natural process by which atmospheric gases trap this major portion, about 80% of the gases are trapping heat energy, and it's in the form of this infrared radiation. There's another planet that's very good at this as well. It's the planet known as Venus, acts in a similar manner. It's capable of trapping even more heat as its atmosphere is 96% carbon dioxide. Remember, carbon dioxide is one of our trace gases in our atmosphere. So you can imagine how much heat would be trapped if 96% of the overall atmosphere is CO2. So CO2 is this greenhouse gas because it's capable of absorbing and emitting infrared radiation, thereby warming the atmosphere. So let's just check for some common understanding. These greenhouse effect gases, these are a list of greenhouse gases. We have carbon dioxide, very good at absorbing infrared radiation and storing it in its bonds. We have water vapor, just plain old moisture in the atmosphere. It's very good at holding and storing infrared radiation in the bonds of its molecule. We have natural gas called methane, which is CH4. CH4 or methane, again a molecule very good at holding energy in its chemical bonds, as well as nitrous oxide, NO. Ozone molecule, we studied last chapter, O3. And chlorofluorocarbons, which you generally see written as CFCs, a center carbon with chlorine, fluorine centered around the carbon. Chlorofluorocarbons are known as CFCs. All of these gases are essential in our atmosphere to trap heat. We all agree that they trap heat. What we don't agree upon, either scientifically or politically, is how much is too much. How much is okay, and how much is actually causing an environmental change. So the greenhouse effect is a natural phenomenon that occurs by these gases that we find in our atmosphere that trap and keep infrared heat energy, which is a good thing because it's creating an ambient temperature to support life on Earth. But global warming occurs when we have these temperatures of what we would consider global temperatures steadily rising from an increased level of the greenhouse gases that we listed on the previous slide. So global temperatures rise pretty much in correlation as the levels of greenhouse gases rise. Global warming is an effect due to increased greenhouse gases. We're gathering evidence, more and more evidence over time. The Earth's atmosphere has naturally changed with climate changes over the past 4.5 billion years. No one argues that there is a cyclic nature to the atmospheric composition and how much greenhouse gases have been present. There's a natural cyclic process where we have high levels and low levels, high levels and low levels. This is not argued that there is a natural process due to volcanic action or weather patterns that bring a high level of gases that are considered greenhouse gases and then lower levels. However, we are noticing, especially in recent years, being the last 20-30 years, that there's been a significant rise in the level of greenhouse gases. So these periodic changes in the shape of the Earth's orbit or the tilt of the Earth's axes, which is the ice age, or even just volcanic action, all of these things have shown changes in the natural level of greenhouse gases. So sun output of energy is 25 to 30% more today than it was a billion years ago. Why? Why are we receiving about a quarter to 1/3 more energy from the sun reaching the Earth than let's say a billion years ago? And how do we know a billion years ago how much was there? Well, this is an interesting chart. We'll get an idea. The last set of data here is from year 2010, and this beginning chart was in the year 1960. And this is up on a mountain. It's actually a volcano, Mauna Loa in Hawaii. And what they started to do is just record carbon dioxide levels and really just considering volcanic action at this particular volcano in Hawaii. And they started to just measure a natural occurrence of CO2. And what would you say is just a general observation? from 1960, and see there's natural fluctuations, but as a general trend, what is the trend that we see? Well, there is a significant rise of carbon dioxide in our atmosphere since 1958 when we started recording at this particular site to after 2010 when we saw this graph created. More than just a natural cycle, we have something else going on. So these natural phenomena will continue to influence Earth's atmosphere and its climate. Volcanoes will always they'll erupt. But we must also assess the role that human activities is playing. I mean, something else has to be going on for that significant rise in CO2. What might that be? Think about the modern industry and the whole industrial age that has taken off from this particular chart, right? The industrial age. How about the levels of carbon dioxide from fossil fuel burning? I mean, we all own cars and drive. The natural gas coming out of petroleum cracking, natural gas placing carbon dioxide in the air. So anytime we take a fuel, and this is a good review from a previous lesson, this is natural gas, but it could be absolutely any hydrocarbon. When a hydrocarbon, which is a fuel, combusts, adds oxygen, we know that the byproducts of combustion are carbon dioxide, a greenhouse gas, and water vapor, which is a greenhouse gas, plus energy, because this is a very exothermic reaction. And so every time we look at this particular combustion, any type of fuel that burns, we are giving a very direct level of carbon dioxide, which is a greenhouse gas, and we're adding in even more greenhouse gas through water vapor. Alrighty, so we're adding and contributing to the amount by any types of transportation and modern industry. So what do we do to obtain data about the composition of our atmosphere back in time? And this is a secret where they take ice core samples. Regions of the planet that have permanent snow cover contain preserved histories of the atmosphere. We have been drilling and collecting ice core samples for over 50 years. What happens is that when we drill out and get this big sample of ice, and literally it's a core, it's a machine that just drills down, drill it back out, and out comes a solid core of ice. Well, in any ice sample, you have air bubbles trapped. And those air bubbles can be analyzed into the composition of each gas present at that particular moment in time. So due to these little trapped air pockets inside of an ice cube, drilling down deep, we go further back in time. Drill down even deeper, you'll get further back in time. So the deeper you drill, the more history you're pulling out of that glacier. And we can analyze the composition of the air pockets and figure out how much carbon dioxide was present those many years ago. And that's what they're showing you here. So we can see this particular glacier, very deep glacier. The further they drill down and can get out an ice core sample, you're drilling down many, many, many years back. And by analysis of these air pockets, they get an idea of just what the compositions of the greenhouse gases were over time. So here's a long time ago, and then we can just see by analyzing the change in the air pockets from deep down to the more current level of ice, you can see the composition of the greenhouse gases changing. And that's what this slide is allowing us to do. Again, this is an ice core over Antarctica is in the squares. Then we started to collect over the Sipple ice core in Antarctica, which is the triangle, so you see some data represented here. And then in the Mauna Loa, which is the volcano in Hawaii, you start to see the red dots here. So this is way back in time, year 1000, this is year 2000, and you can start to see the concentration of CO2 significantly change. Pretty level through these, approximately 1,000 years. And then in the green, you start to see it rise, and then of course dramatically rise in the last, from like 1900 to 2000 and above. Another interesting graph is kind of looking here. This is again year 1000, year 20,000, or year 2000 years ago. So you're looking here at parts per million of CO2 concentration. So the ice core shows data back 400,000 years, while other ice cores can even go back further. And what we're gathering is that, significantly, we can all agree that there are ice age cycles. At sometimes we have high levels of CO2 and sometimes we have low levels of CO2, that the atmosphere definitely undergoes cycles, and it's based on weather patterns and volcanic eruptions, what might be contributing to CO2. Except, again, this is like present day, 0 years back, 100 years back, 200 years back, and so forth. And these are thousands of years ago. You can definitely see a systematic rise in CO2 levels. That the normal chain of events with the up and down cycles has significantly changed. And why? What's been going on since 1800 to the present day? What's been going on that wasn't going on to prior? And certainly we can all agree that it's man-made activity. It's our industrial age, it's burning of fossil fuels, all of those things we do that contribute to a carbon footprint in the atmosphere that contributes to greenhouse gases and the warming of our environment. Again, the red bar indicates average temperatures for the year, while the black bars show the range for the year. So again, the range from hot to cold, but these are overall averages. And so look at year 2000, significantly higher, and again, this is probably 2010, even past, and compare that to the year 1880. We all agree there's natural cycles, but notice what happens when carbon dioxide levels begin to rise. The temperatures also rise. There is a direct correlation between CO2 levels and atmospheric temperature. So global temperatures for the year 2011 in Celsius degree. The red, of course, is the warmest. Blue would be the coldest. And you can see the most dramatic changes have occurred at the higher latitudes. So again, where volcanic eruption occurs and so forth, but also due to weather patterns where the carbon dioxide gases have been, with the jet stream, will flow and congregate over our ice caps. We'll look at one more graph together presented in your text. The concentration of carbon dioxide in blue related to the temperature correlated in red. So what is this graph showing us? If you see the temperature recorded in red, and again I see just a cycle of things going. Here's present day, this is 100,000 years back, 200,000 years back, and so forth. And the CO2 levels, don't you see how nicely they line up with a cause and effect? So now I'm noticing that when CO2 levels dramatically rise, what should we expect? This is years ago. What should we expect in the future when the CO2 levels rise? What would you expect to see this red line start to do in terms of temperature? And again, if we're still arguing, do we care? Does a 5-degree change in the overall atmosphere really matter? Does a 10-degree change in the fluctuation of the weather really matter? Well, that's where the scientists and the politicians will begin to argue differently. Let's pause here, give you time to process our first lesson before we go into molecules and how they shape up, talking about the shape of molecules and how they contribute into storing bond energy from the sun. When ready, come on back for lesson number 2.